Hi everyone, welcome to the video lecture on linear optimization or linear programming. Both those terms are used interchangeably in this context. For this video lecture, we're going to talk about how to formulate a linear optimization model, how to solve it in Solver in Excel, and we're also going to talk about some of the more common applications of linear programming. So linear programming was initially developed to help the military with some of their operations and decision making, and soon the models started being used in the business scenario as well. Optimization models can be linear or nonlinear, but for this particular class, we're only going to focus on linear models. For an optimization model to be linear, the first assumption that we need to satisfy is that all the equations in our model need to be linear in nature. So that includes your objective function, your constraint equations, as well as your decision variables. Management decisions in many organizations involve trying to make the most effective use of resources. Resources typically include machinery, labor, money, time, warehouse space, or raw material. And these resources can be used to manufacture products, or they can be used to provide services. So, for example, the products could be computers, automobiles, furniture, clothing, etc. And services could be package delivery, health services, advertising policies, investment allocation decisions. In all sorts of resource allocation situations, the manager must sift through several thousand decision choices or alternatives to identify the best or the optimal choice. The most widely used decision modeling technique designed to help managers in this process is called mathematical programming. The term mathematical programming is somewhat misleading because this modeling technique requires no advanced mathematical ability. It just uses basic algebra and has nothing whatsoever to do with computer software programming. So there is no coding involved. In the world of decision modeling, programming refers to setting up and solving a problem mathematically. Within the broad topic of mathematical programming, the most widely used modeling technique designed to help managers in planning and decision making is linear programming. So we're going to talk about how, why, and where an LP model works, and we're going to look at how to get a solution for an LP model using the Excel solver. So an LP model basically has the same structure. Whatever the application that it's being used for, the structure of the problem still remains the same. Every optimization problem that you're going to model and solve is going to be around a certain goal. This goal is what we refer to as the objective function. And that goal could be to maximize something, for example, profits, or the return on investment, or it could also be to minimize something. So it could be the cost, any type of cost, inventory cost, production cost, advertising cost, or it could also be used to minimize time, minimize the number of employees that are required. And this goal needs to be satisfied within a set of restrictions, which we call constraints. Now, as I said earlier, optimization models can be linear or nonlinear, but we're going to focus on just linear models for now. There are plenty of applications for linear programming models. It's most widely used in the production environment, where you have to decide how much of each product to produce. It's also used widely in operations. A typical example is if a manufacturer wants to develop a production schedule and an inventory policy that satisfies the demand but at the same time minimizes the total production and inventory costs. Or you could formulate an LP model to help you decide what is the optimal money allocation to different types of investment options that you have to form a portfolio that maximizes the return on your investment. It can also be used in the marketing scenario where you could use it to best allocate a fixed advertising budget among different options that are available to you. So for example, web, radio, social media, television, etc. Companies also use it in a transportation scenario where they optimize to find the minimum transportation cost and still get the product delivered to its customers from the different warehouses where it stores the product. So whenever we're formulating an LP model, we have to consider some of the basic assumptions of an LP model. Technically, there are 4 assumptions of an LP model which you should be aware of. The first one is that we assume that conditions of certainty exist. That is, the number used in the objective function and the constraints are known with 100% certainty and do not change during the period that they're being studied. We also assume that proportionality exists in the objective function and constraints. This means that if production of 1 unit of product uses 3 hours of a particular resource, then making 10 units of that product produces 30 hours of that resource. The third assumption deals with additivity, which means that the total of all activities equals the sum of the individual activities. So for example, if an objective is to maximize profit, which is $8 per unit of the first product made, plus $3 per unit of the second product made, and if 1 unit of product is actually produced, the profit contribution of $8 and $3 must add up to the sum of $11. The fourth assumption is that we make the divisibility assumption, that solutions need not to be whole numbers, so they can be fractional values. If a fraction of a product cannot be produced, then in that case we would have to use an integer programming problem, but that's an advanced version of the model, and for our analysis we're only going to assume that fractional values are acceptable. If we get a solution in decimals, that's okay with us. Whenever we're trying to solve an LP problem, there are 3 basic steps that we need to follow. And those 3 steps are what we call the problem formulation of the model. And in the problem formulation phase of the model, the 3 steps that we need to follow include deciding on what your decision variables are going to be. Decision variables represent the unknown entities in the problem. So basically, they are exactly what we are solving the problem for. They are the solution that we're looking at. Decision variables are expressed in the problems using alphanumeric symbols. So when writing the formulation on paper, it is convenient to express the decision variables using simple, easy to understand names. For example, the number of tables to be produced can be denoted by names such as T, or tables, or X1. And the number of chairs to be produced can be denoted by C, or they can just be called chairs, or X2. The second step is to identify what your objective function is going to be. The objective function states the goal of a problem. That is, why are we trying to solve this problem? An LP model must have a single objective function, In most business-oriented LP models, the objective is to either maximize profit or minimize cost. The goal in this step is to express the profit or cost in terms of the decision variables defined earlier. And finally, the third step is to identify your constraint equations. Constraints denote the conditions that prevent us from selecting any value we please for the decision variables. An LP model should have as many constraints as necessary to accurately describe the problem scenario. Each constraint is expressed as a mathematical expression and can be independent of the other constraints in the model. Let's take a look at an example for an LP model. This is the same example that is given in the book. The company that we are solving this problem for is called PAR Incorporated, which is a small manufacturer of golf equipment and supplies, and their management team has decided to move into the market for medium and high-priced golf bags. Now, PAR's distributor is enthusiastic about the new product line and has agreed to buy all of the golf bags that PAR produces over the next 3 months. Now, through an investigation of the steps involved in the manufacturing of a golf management has determined that each golf bag produced will require the following operations: cutting and dyeing, sewing, finishing, inspection, and packaging. So the input variables that are given to you in this case are for the two types of products that they wish to produce. One is a standard golf bag and the other one is a deluxe golf bag. And in this box over here, they've given you the input requirements for each type of product. So for example, if we take a look at this first row of input values, the way you're going to read it is that it requires 0.7 hours of production time in the cutting and dyeing stage for a standard golf bag to be produced. And for a deluxe bag, it requires 1 hour of cutting and dyeing for a deluxe golf bag to be produced. Similarly, the standard bag requires 1 hour of finishing time, and the deluxe bag requires 0.67 hours of finishing hours to be produced. So now that we have the inputs in front of us, we need to decide what our decision variables are going to be. So I'll put those down here. Our decision variable is to decide on the production quantity for each type of bag. So the decision variables for our model would be represented by S, which we are using to help us to note the standard golf bag, and D, which we are using to help us to note the deluxe golf bag. These are the only two types of variables that we're considering at this stage right now. And I'm going to leave these two cells that I've highlighted as blank for now, because this is where the solution would show up. So I want to assign these two cells as my decision variable cells. Okay, and I've highlighted them in yellow because I like color coding my Excel sheet. That way, when I move on to the solver window, I know which colors represent which values, so I can simply put them in the designated prompt spaces. So now that we have decided on our decision variables, the next step is to define our objective function, which is our goal. Now, given the data for this particular problem, you've been given the profit contribution for each type of product, which means that they're giving you a hint that this is a maximization problem because you would want to maximize total profit. So I'm going to label this cell total profit, and I will color code it in green so that I know this is where I need to store my objective function. And because this is a maximization problem, I like to put a max in front of it so that I can remember it. This is also useful when you open up your Excel sheet after a long time. It helps you read it easily. So now our objective function needs to be defined in terms of the decision variables that we just defined for our model. So because of all the assumptions that were mentioned earlier in the lecture, we're assuming that each quantity of standard golf bags will contribute $10 towards the total profit, and each quantity of deluxe golf bags will contribute $9 to the final profit. So if I write it down as an equation, that just means that my total profit is equal to 10S plus 9D. S and D here represent the quantity that we're going to produce of each type of these golf bags that we already defined. So in order to put this expression in an Excel format so that Excel knows what the relationship between all these input variables and our decision variables is, I'm going to use the sum product function to do that. Oh, sorry. So for the sum product function, you need at least two arguments. So you basically want the sum product of the input coefficients that have been given to you, 10 and 9 in this case, with the unknown variables S and D. So I'm going to select S and D first, comma, select the coefficients for S and D. Now here you need to keep in mind that the order does not matter. I can select the cells with the profit coefficients first and then select the cells where S and D values will be stored. So these two can be swapped. It doesn't matter. However, the sequence or the order within these arrays need to be the same. So if I'm putting S first, then I need to put the profit contribution for S first, and then D after, so the profit contribution for D after. So once I've added my sum product function, I can press enter here. Obviously it's going to show 0 now because I don't have any numbers in the cells S and D yet. Obviously you can also just type this out by multiplying 10 with S and adding the product of D with 9 to it, but the sum product function just generally makes it easier to put in the equation easily. So now that we've added our objective function, we need to decide what the constraints are. Now the constraints in this case, if you look at the input data that has been given to us, would be around these 4 resources, and the resources for us are the total time in hours available for each of these stages of production. So each of these stages of production are going to have a constraint equation of their own. So I'm going to just copy these stages and put them down here under constraints. This just makes sure that the constraint equations are given in the model for each production stage. So over here, what you can see is that in the input data, each standard bag takes 0.7 hours and each deluxe bag takes 1 hour to complete. And in total, we have 630 hours available for this specific production stage. So if I put this down as a mathematical expression, this basically means that 0.7S plus 1D needs to be less than or equal to 630. Okay, that's our first constraint equation that we need to put as a part of our model. The reason why I used less than or equal to here is that I have a total of 630 hours available for this stage. As a part of the optimal solution, I can either use all of those 630 hours, or I can use some value lower than this, but I cannot go beyond this because I don't have any resources available beyond this number. So the way I'm going to put it in the Excel sheet is that I'll put the coefficients separately. So 0.7 under S and 1 under D. And here I'm going to create the left-hand side of my equation. So I'll label this column as LHS, standing for left-hand side. And I'm going to again use the sum product function that I used earlier, where I'm going to calculate the sum product of these coefficients with our variable cells, and press enter here. Again, it's going to be 0 because we don't have any numbers under S and D. And here in this column, I will put the sign for this constraint equation, which in this case is less than or equal to. And in the next column, I would put the right-hand side of the equation, which is the availability of this particular resource. In this case, it's 630. So now the way I'm putting down the steps here, all of these steps are not required. So for example, I don't need to put the sign again. I don't need to put the right-hand side again if it's already there in the Excel sheet. But the reason why I'm doing it, because we're learning about this, so I'm breaking down all of the steps into as small steps as possible so that it's clearer when you're trying to understand your first LP problem. So the same way for sewing, our constraint equation would be 0.5 S plus 0.83D, and that needs to be less than or equal to 600. So again, I will start populating my constraints in my Excel sheet. So coefficients first, 0.5, 0.833. Actually, let me just copy that from up top here so that I get the decimal places right. And again, I will use the left-hand side to put down the relationship between these coefficients and our decision variables. Now, there's an easier way to do this. I can simply drag this formula down that I had put in D18 and drag it down for all my constraints. But because I have not fixed my decision variable cells in this formula, when I drag it down, Excel is going to use relative copying. So it's going to change the cell references here relative to the row that I'm dragging it for. So because I want to keep S and D constant, I'm going to put $signs in front of both these cell references. This will make these two cells constant when I copy the formula down. So press enter. That does not change anything in the operations of your formula. It's just for constant referencing. So now I'm just going to drag it down, and I'll drag it down so that it covers all 4 of my constraints. And if I click on the last one, you see that the formula has been updated. The blue cells are the updated cell references. The red cells remain constant. Let's complete all of our constraint equations now. The third constraint would be 1s plus 0.67d, and that needs to be less than or equal to 708 hours. And finally, the fourth one for inspection and packaging, 0.1s plus 0.25d has to be less than or equal to 135. Now, keep in mind that for this particular example, all our constraint equations are less than or equal to. That's not the case with all problems. Sometimes you would have greater than or equal to constraints as well. So for example, if you had a demand constraint that the production needs to satisfy at least the minimum demand of 100 units of S and 250 units of D, then this would be a greater than or equal to constraint instead of a less than or equal to constraint. So let's put down our coefficients here. So under finishing, we would put 1 under S and 0.67 under D, and then for inspection and packaging, I'm just going to put the values as they're given above. I don't need to worry about these. All these formulas are already in the left-hand side, and just to remind me that the next time I open this Excel sheet that these are the calculated values. These are the actual values of how much of each of these resources that I'm going to be using out of the total. So that's why I put them in blue here. And let me just make some formatting here so that it's easy to read. Okay, and I can simply drag this down because all of my constraints are less than or equal to constraints. For each of my constraint equations, I need to add the right-hand side values of the equations, so 600, 708, and 135. Now my model is in a format which is complete, so that now I can go to Excel's solver so that I can solve for the solution for this particular model. To do that, you can simply go to data, and when you click on data in your ribbon up top, you should see the option for solver right at the top right hand side. If you don't see this option for solver, you will have to go to the options and add the add-in for solver to your Excel workbook. I will post the instructions for this for you in case you don't see this part on your Excel sheet. So I'll post the instructions for how to add the solver add-in on your Excel sheets on Canvas. So let's open up our solver window. Okay, so this is what the solver window looks like, and now I'm going to start putting in the different values in here in my solver window. So the first value that you need to input here is the objective function cell reference, and this is where the color coding comes in handy. Is I know that the cell that I highlighted in green is what needs to go here, so I'll put the cell reference for that particular cell where I've stored my objective function value in the set objective box. Here I can decide whether I want to maximize, minimize, or set my objective function to a specific value. Since this is a profit maximization problem, I'll click max. Changing variables are what Excel call your decision variable. So that's the name that Excel gives your decision variables. And this is again where the color coding is going to be beneficial. I know that the yellow cells are my changing variables, so I put the references to the yellow cells here. And now I will add my constraints. Now for the constraints, there's a nice feature here in Solver that you can put in all the constraints which have the same sign as a one line item instead of having to put each constraint separately. Obviously you can do that as well, but doing it like this makes the process more efficient and simpler as well. So I'll add a constraint. When I click on add, this is what pops up. So now you can see that the left hand side and the right hand side, the way I put it in the Excel sheet, is going to help me put it in the solver window as well. So I know that the left-hand side values go here to the left. I have to select the sign, which is the less than or equal to, and then here I select the right-hand side values and press OK. And now that I have my constraints in there as a line item, my solver is ready to run. One thing that you should keep in mind is if you have constraints which have more than one type of inequality in there, you would have to put that as a separate line item. So you would, let's say if there was a greater than or equal to constraint, you would click add here and add that additional constraint as a separate line here. Make sure that you check the make unconstrained variables non-negative, because that is going to make sure that the values of your decision variables are not negative, because in a business environment, negative values for production doesn't really make sense. I mean, you can theoretically call it backlogging, but for our case, to make this model simpler to read, we'll just check this every time. Now, when you select a solving method, Excel gives you three options. We're going to use the simplex LP algorithm to help us get the solution. And press solve here. And then once Excel has found the solution, it's going to pop up with this window. Here you are going to select keep solver window. Excel also generates additional reports about your solution. This can help you understand the sensitivity of your solution to the different input values. So you can select each of these additional reports. When you select these and press OK, these reports are generated automatically as a separate worksheet in your same workbook. So for now, let's not select these and just solve it as it is and press OK. So now you can see that Solver has populated the solution for us. The maximum profit that we can make with the given resources is 7,668, and that means we need to produce 540 standard bags and 252 deluxe bags. This is the most optimal combination of the production quantity for each of these products that will give us the highest profit, given that we are operating in an environment where we only have these many hours for each of these stages available.